When we look up at the cosmos, we see a universe that's filled with billions and billions of galaxies, each of them home to billions and billions of stars shining back down upon us.
But despite the vastness, from here it looks a lonely place. Are we the only life that looks up at the sky at night, or somewhere else, around some other twinkling star? Are there other beings doing the same?
Remarkably, we're making progress towards answering that question. In the last few years, we've discovered our galaxy is teeming with planets, alien worlds in almost unimaginable variety.
And for the first time, we're actually getting a glimpse of what these worlds are really like. But the question is, can any of them harbour life? Come with us on a journey through the galaxy as we hunt for ET.
Welcome to the Sky at Night. Our search for alien life doesn't have to be limited to waiting for extraterrestrials to give us a call. New astronomical techniques have enabled amazing discoveries, taking us closer to finding life out there than we've ever been.
Some of the most advanced work in studying alien atmospheres is done here at Exeter University. In this programme, we're going to be pushing at the boundaries of science in the search for alien life.
Coming up, how do we define life, and would we recognise it if we saw it? Adam Rutherford investigates.
So when we look at other atmospheres, if we see CFCs in their atmospheres, then we know there's some kind of a technological civilization on that planet.
These are sunsets, seen from other planets, orbiting distant stars. What can they tell us about the potential for extraterrestrial life?
And how many alien civilizations could there be out there?
If we looked up into the night sky, we'd expect to see 5. And that includes us as well, so we'd actually expect to see 4.
Plus, as autumn comes upon us, Pete is looking at one of the great spectacles of the night sky, Andromeda.
If we want to discover life beyond our solar system, there are certain things we should look for. And the first is a planet, preferably one rather like the Earth, with liquid water, continents and a nice atmosphere. And this hunt for extrasolar planets, or exoplanets, is beginning to pay off. Until 1995, despite decades of searching, our solar system was the only one that we knew about. Then, suddenly, everything changed when 2 astronomers in Geneva announced the discovery of this planet. Rapidly orbiting and weighing about half the mass of Jupiter, it goes round the star 51 Pegasi, just 50 light-years from Earth. But since then, the discoveries have come thick and fast, and we found all sorts of unexpected planets. And then there's HD 209458b, a planet larger than Jupiter, which is so close to its parent star that it's losing its atmosphere. More than 10,000 tons a second of hydrogen are swept off in a long train, rather like a comet's tail. And just over 150 light-years from Earth, there's a planet in a system with 3 suns, creating this astonishing sight from a hypothetical moon. But none of these exotic worlds could support life. What we need is a planet in the Goldilocks zone, not too hot and not too cold, but just right, able to support liquid water and therefore maybe life on its surface. We found a number of planets that should be rocky. But the candidate that's closest to our own Earth is this one, Kepler 186f. It was discovered in April this year and is the first planet we found that's close in size to Earth and that's the right distance from its sun to maybe harbour life. In total, we've now discovered 1,516 exoplanets, nearly half of them in the past year, and the hunt continues.
So we can find alien worlds. But what about the aliens themselves? Do any of these planets harbour life? It's a tantalising question, and I wonder, even if we found life, would we recognise it? Adam Rutherford is investigating.
Everywhere you look on our planet, there is life. And it comes in all shapes and sizes. From the tiniest bacteria to the blue whale to the fungi that spreads over hundreds of acres, there seems to be an almost endless variety to life on Earth. And this astonishing variety raises a really interesting question. How do we actually define life? This is a question we really have to answer if we want to look for life off-world. We instinctively understand what life is. We know it when we see it. The tree is alive, but the clouds above are not. But codifying these differences isn't easy. What's needed are a series of testable criteria that fit all living things and exclude all non-living things. One way is to look at how life behaves. There are certain behaviours that all life seems to display, such as movement, growth, respiration, and in particular, reproduction. But these characteristics might not always be exclusive to life. Take a flame, for example. It starts with a spark. And as the flame gets bigger and bigger, it consumes fuel in the form of oxygen from the air and carbon from the wick. If you blow on it, it responds, and it produces waste in the form of smoke and gas. Now, these are all the types of things that we associate with living organisms. And it also does something which is a lot like reproducing. You can use one flame to create another, and another, and another, and so on. So the question is a flame alive? Of course, the answer to this is no. One of the reasons is that the flame doesn't contain any information. And information seems to be a key characteristic of life. All life reproduces itself, and when it does so, it passes on information from generation to generation. Now, that information is encoded in DNA, and every time a cell divides, it passes it on from cell to cell, from parent to offspring. But does the presence of DNA define what life is everywhere in the universe? Well, for me, the answer is no. Yes, DNA is universal amongst all living things on Earth. But it doesn't help us to understand how life began in the first place. It misses a key process that makes living things alive. DNA replication requires energy, and when we look at how cells generate that energy, it is a more fundamental process than replication. Whilst DNA is how life replicates here on Earth, it might not be the case elsewhere. But there is a process that should be universal. Life is a chemical reaction, a process of extracting energy from the environment and using it to sustain itself. A process we call metabolism. And this is the key to defining life. You can see it in action here in the lab. In this jar is water and a plant called Ageria. Now, the plant consumes energy in the form of light and uses it in the production of glucose. Now, as a byproduct of that metabolic process, it produces oxygen. And if we look very closely, we should be able to see tiny bubbles of oxygen coming off the plant. There you go. Now, this is a process that all plants do. It's called photosynthesis. They extract energy from the environment to create something new. In this case, using light to convert carbon dioxide and water into sugars. And then the plant uses that sugar to power complex living processes. Without metabolism, there would be no energy to sustain life and no energy to reproduce. And luckily, metabolism leaves a trail of evidence behind it. In fact, the oxygen that fills our atmosphere was created by life. So, forget about radio signals from ET. If we really want to find signs of life, we should be looking at the atmospheres of exoplanets. And it is possible to do this by analysing light that passes through the atmospheres of distant planets to reveal what they're made of. To understand what signs we should look out for, I'm meeting Louisa Preston. If we were to look at the Earth from space, would we be able to tell that there is life on Earth?
Yes, we'd be able to see oxygen, be able to see methane, carbon dioxide. We also can look at the Earth whilst we're standing on it. The sunlight hits the atmosphere of the Earth and it gets reflected away, and it hits the moon, and then actually the moon reflects it back to us. So we can observe ourselves. It's called Earthshine.
So we look at the moon and we can tell that there's life on Earth.
Yes.
How do we then transfer that into looking for life in exoplanets, in other planets?
Well, because we know that the atmosphere can harbour these different types of molecules that life creates, we can look for exactly the same thing when we look at exoplanets. But we just have to figure out what the exact right molecules are. So oxygen is definitely a biosignature that we would look for on another planet. Problem is, it can be made from non-biological ways. Same with methane. So we have to be careful of these false positives, we call them.
So is it that we're looking for a particular combination of those gases in the atmosphere, so the right amount of methane, the right amount of oxygen?
Sure, it's not the right amount exactly. So it's more a disequilibrium idea. So there could be a bit of oxygen, there could be a bit of methane. We want to see an excessive amount because oxygen and methane are very short-lived. They can degrade very quickly, react with other products, react with each other. But if there's life, it will keep pumping it into the atmosphere, so you'll see more of it than you would expect. And the best thing is to find them together.
Now, these are signatures of simple life. What about us? What should we be looking for if we were looking for intelligent life?
Sadly, we'll be looking for pollutants. So we all hear about CFCs and the hole in the ozone layer. They are really long-lived, and they also cannot be created naturally. They are created by us and by intelligent life. So when we look at other atmospheres, if we see CFCs in their atmospheres, then we know there's some kind of a technological civilization on that planet.
Just CFCs? I mean, wouldn't that just indicate that people are using deodorants on those planets?
If we see just CFCs, it might indicate that there was once an advanced civilization there that's created it. What would be amazing to find would actually to be find oxygen as well as CFCs, because that means actually there might be a civilization there right now.
That is using deodorants and fridges
And
but still
hairspray.
alive.
Yes.
Well, good luck with the hunt, thank you.
So the good news is we can detect signs of alien life in the atmosphere of exoplanets. But the bad news is that they're so far away, how can we possibly pick up the signal? Well, that's just what they specialise in here at Exeter University. Chris is talking to Hannah Wakeford, who is part of that team.
So most of the planets that we know about have been found via the transit method. How does that work?
So if you imagine that this is our star that we're looking at, we're seeing the light from that star. But if you put a planet in orbit around that, as it passes in front of the star, it's going to steadily block out that light. So we're going to see a change in the amount of light we're observing. And it's about a 1% change in the amount of light. So imagine a mosquito flying in front of a lamppost 1 kilometre to 1,000 kilometres away. It's a very small change in the amount of light. But as that planet passes in front, it's blocking it out. So that allows us to detect these planets. And it also allows us to kind of see any starlight that's shining through the atmosphere. And the ones that we're looking at the moment are called hot Jupiters. And these are mostly gas giants. So they have really big atmospheres. And that means that we're seeing a lot of the light shining through that atmosphere. And we can tell you loads of things about them.
I think one way to understand what's going on there is to think about what that would look like from the planet itself.
There's a couple of planets that we've got a synthetic sunset as such from that planet. This planet here, HD 189733b, is an observation that looks very much like what the Earth would. And that's because the atmosphere of this planet is scattering the blue light. So like the Earth's atmosphere scatters the blue light, which is why we have a blue sky, which causes the red sunset, you get the same thing. And this is another one. This is HD 209458b. You can see that it's a completely alien sunset. And that's because there's sodium in the atmosphere of this planet. We've detected sodium in the atmosphere by the amount of light it blocks out at a certain wavelength. It's not just sodium that we're trying to detect, we're also trying to detect potassium and water in the atmospheres of these planets.
What about the weather on these planets? We talk about Jupiter and you think of the bands and the clouds and the storms that are going on. Do we know anything about these planets and whether they have similar weather?
Yeah, so from the transit as well, from the light shining through the atmosphere, we can determine what kind of structure it's passing through. So if it's passing through a gas, then it will show the light will interact in a certain way. But if there's a solid particle in the way, if there's something solid blocking it, like a rain droplet, then the light bounces through that solid droplet in a different way. And that allows us to detect whether there are solid particles in that atmosphere.
So we've got to the point where these hot Jupiters are worlds with cloud, with wind, with sodium and potassium in their atmosphere, but what we really care about are terrestrial planets. Is there any hope there of using these techniques to work out what their atmospheres are like?
Yeah, and everything that we're learning at the moment, every technique that we're doing has been developed since the first observation of a transiting planet in 2002, is going to be used to look at these smaller worlds. And that means as soon as we get the technology, then we'll be able to tell you for certain that these techniques are correct, they are working. We've tested them on these massive planets, and we have an understanding of how they work, and that's really important. So we're still in the first stages, but it's definitely in our future.
Well, we'll look forward to those results. I hope we'll come back many times before then and tell us what's going on. Thank you very much.
Thank you.
The reason there's been such a boom in exoplanet detection in the last few years has mainly been down to one mission, the Kepler Space Telescope. It alone has detected 978 new planets so far. Launched in 2009, it has been searching a star-rich patch of sky. But in May 2013, the spacecraft broke down. Two of its reaction wheels had failed. These are the gyroscopes that are used to orientate the spacecraft. Without them, it couldn't remain locked on its target. But in the last few months, the mission has received a new lease of life due to some ingenious lateral thinking. The team worked out that they could use the force exerted by sunlight hitting the spacecraft to stabilize it. Light exerts a pressure on any object it falls on. As photons hit a surface, they transfer some of their momentum to it. It's a tiny force, but in the frictionless, near vacuum of space, it has an effect. The Kepler scientists are using this to their advantage. Now, it just so happens that the spacecraft is symmetrical from one angle. Now, if the remaining reaction wheels can keep the spacecraft at that angle, then the solar pressure hitting the panels will keep it in balance. But for it to work, they have to be extremely accurate. The slightest misalignment will cause the spacecraft to spin rather than stabilizing it. But early tests look promising, and Kepler is once again looking for alien worlds.
Next up, Pete with his highlights of what to see in this month's night sky. But first, here are his tips for capturing the full magnificence of one of the largest objects on view.
As we enter the autumn, the nights are getting longer and longer, and that means it's a perfect time to start doing some stargazing. Now, one of the best objects to look for at this time of year is the Andromeda Galaxy.
Like our own galaxy, Andromeda is a spiral. It's 2.5 million light years away, making it one of the furthest objects it's possible to view with the naked eye.
Now, with a reasonably dark, moonless sky, it should look like a faint, elongated smudge. But when you look at Andromeda, you may not be seeing the entire galaxy.
The central core stands out much more clearly than the rest of the galaxy, and is what many people see. But some of the best views of Andromeda come from photographing it, and depending on how you do it, its appearance can change dramatically.
Now, you can see this for yourself by taking a series of pictures and varying the exposures between each. Now, I'm going to start off with a relatively short exposure length of about 30 seconds or so. Now, what you can see here is very similar to what you'd see with the naked eye. So that's just picked out the core of the galaxy there.
As we increase the exposure time, more details start to come out. Past 60 seconds, the galaxy starts to take on a sharp edge, which is the result of a dust lane blocking starlight. As we up the exposure, the Andromeda Galaxy gets bigger and bigger.
Now, in my earlier 30-second exposure shot, all I picked out really was the core of the galaxy. But now in this longer exposure, I can actually see those beautiful spiral arms either side of the core quite clearly there.
However you view it, Andromeda is a magnificent sight, and if you do capture its true size, it appears 6 times the width of a full moon.
The Andromeda Galaxy is really easy to find in the night sky. So here's my guide to finding it and other highlights happening this month.
A quick way to locate the Andromeda Galaxy, which is in the constellation of the same name, is to first identify the W-shaped pattern of Cassiopeia. The right half of the W is like an arrow pointing down towards the star Merak in the constellation of Andromeda. Look up slightly from Merak to locate the fainter Mu Andromedae, and a little further up still to find the even fainter star Nu Andromedae. The Andromeda Galaxy sits slightly above and slightly right of Nu. Also this month, just before sunrise on the 20th, you'll be greeted by the magnificent sight of Jupiter next to a thin, waning crescent moon in the eastern part of the sky. Finally, on the 28th, look low down in the southwest about an hour after sunset to see planet Mars close to the similar brightness star Antares in Scorpius. The name Antares literally means the rival of Mars because it's supposed to look just like the red planet. Now's your chance to check whether it really deserves that title.
Now, back to the hunt for ET. So we've talked about what life is and where it can exist, but what are the odds of us actually finding life out in the cosmos? 53 years ago, astrobiologist Frank Drake penned his famous equation, which aimed at answering precisely this question. But we know much more about the universe now than we did then, and Maggie's been catching up with astrobiologist and alien hunter Duncan Forgan to find out how far we've got.
The Drake equation is made up of a series of conditions that need to be met for us to communicate with alien life. Each letter represents one of these factors, such as how many stars have planets orbiting them, or how many of these planets support life. Duncan is going to help me fill in these figures based on the latest research.
When we start populating this, how does that work?
Well, it gets a bit tricky to populate. I mean, when we start on the left-hand side, we're actually in the bits that we know quite well. And as we go across the terms, we get closer and closer to the edge of our current understanding, and then we go past it into the unknown.
Okay, well, let's start at the beginning. Let's start with R.
Okay, so
the rate of star formation in our galaxy.
So the rate of star formation in our galaxy, the number we expect to see per year, is somewhere between about 5 and 7. So why don't we start with just with 5 per year? That's a nice round number.
Yes, and conservative.
Conservative. So FG, the number of stars that have a planet, that number has changed a lot, obviously, because we now know a lot about exoplanets that we didn't know 20 years ago. We think now that this particular F term is in fact 1.
So we're not assuming that all stars in the galaxy have planets, but many stars have multiple planets.
That's right.
And so that keeps that at 1.
Yes.
And that's sort of recent findings from what we're doing with the exoplanets at the moment.
Yeah, this is cutting edge research right here.
The next 2 terms relate to the number of those planets that can support life, that are habitable.
So moving on to FP.
So FP is where it starts to get a bit trickier for us, because now we have to start thinking about what the word habitable means. And
yes.
We don't have a good strict definition of what life is, so that actually hampers our ability to then say, what does life like?
Yeah.
So we're really, if you want to put like the frontier of science, if you like, at this point, then it kind of exists about here in this line. Okay, right. So we're now at this point where we've pushed our knowledge of the terms in Drake's equation all the way to here.
I suppose when Drake started, we were back here.
Yeah. So Drake wrote this equation in 1961, and we only had 1 term, but we've managed to push these things. And really, just in the last couple of years, in the last decade, we've really gone from, we were kind of here with the first detection of exoplanets about 20 years ago, and with the Kepler Space Telescope and other missions like it, we're really pushing in this direction now, and we're picking up a bit of speed.
But from here on in, it really does become guesswork. There's how frequently does life form? And the likelihood of that life being intelligent. But what do we mean by intelligence?
There are many definitions of intelligence, and in this very strict definition of the sense, really we became intelligent when we started sending strong radio signals out into space. And that was really only about 100 years ago. So we've not been intelligent, quote unquote, for very long.
Yes. And the last term, L.
So the last term L is how long we expect to see that signal. And what that really means is how long do we expect the civilization to last?
So you need to get that overlap of intelligence
Yep.
to make that communication.
That's a very good point. And it kind of demonstrates that the galaxy is big in space, but it's also big in time. There's lots of time in the galaxy. So you've got to make sure that if you want two civilizations to have a conversation, they have to be close in space and close in time at the same time.
Duncan speculates that the average civilization will be able to communicate for 1,000 years. So, what's the answer to the equation?
So there's about 5.
5. But that's in the whole of the galaxy.
Now that's at any one instant. If we looked up into the night sky, we'd expect to see 5. And that includes us as well. So we'd actually expect to see 4.
I think that fundamentally it's a question we really want to answer, and it's something that people have always wanted to answer.
And I think for me, that's the beauty of this equation, is that in some way it kind of encapsulates all of mankind's search to understand itself as well as understanding its place in the universe.
Yes.
So you start with the terms that are to do with astronomy and to do with physics and chemistry, and then you get onto the planetary sciences and the geology, and then you have the biology, and then as you get to the very end, then you have to start thinking about the things that aren't the hard sciences, but the social sciences. You have to think about the psychology of life. You have to think about anthropology. The whole academic discipline of mankind is somehow encapsulated in these 8 letters.
But I've never seen it in that way, so thank you very much. It's
thank
a
you.
new perspective on the Drake equation.
Thank you.
That's about it for this month, but we wanted to let you know about a fabulous competition being run by Blue Peter to design the official mission patch for British astronaut Tim Peake's visit to the International Space Station.
You need to be between the ages of 6 to 15 to enter. Now, if you want more details of the competition and their terms and conditions, please go to our website. The competition closes midday on the 26th of September, so do get your designs in.
We can't leave you without mentioning Rosetta, ESA's comet-chasing probe, now just 50 kilometers from Cheremeov-Gerasimenko, and getting ready for the touchdown of the Philae lander in just a few months' time.
ESA have already identified 5 potential landing sites, which you can see up here. And they'll narrow that down to 2 in the next few weeks. But my favourite landing site is definitely J, because it's accessible and this has been travelling for so long, I just want it to all go right. So go for the easy picking.
I think that's an engineer's view. As a scientist, I'm a big fan of what they're calling Site A, which is on the larger lobe of the comet, the body of the rubber duck, if you think of the thing as a rubber duck. Land there and you get a view of both parts of the comet, and I think that would be really exciting.
Good, but go for the easy pickings. But we'll be finding out exactly what they choose in the next few weeks.
When we come back next month, we'll be talking about the outer edges of the solar system. It's ice giants, Uranus and Neptune.
In the meantime, get outside and get looking up.
Good night.
Keep those eyes to the skies next tonight and settle in for A Comet's Tale here on BBC4 Next. And then rock turns to metal in Heavy Metal Britannia. Catch up with this week's Music Night programmes in an hour.